This is where we are going to end our discussion of combinational logic circuits, and we will also begin our next lecture discussing sequential logic circuits. But just to review the difference between the two, a combinational logic circuit always gives the same output for a given set of inputs. So for example, an adder always generates a sum and a carry regardless of the previous inputs. It's only based upon the current inputs. Sequential logic circuits, they store information from one state, that's a critical term, from one state to the next. What is the smallest increment of change from one state to the next? In a processor, it's one clock cycle. So it's pretty quick, unbelievably quick. The amount of time is billionths of a second, but we'll get to there as we move forward. In the lecture section for this week's module in Canvas, I placed a link to a YouTube video I found that's really good. It describes the RS latch, also called the SR latch. He uses that term. It's the same. And I'd like you to pause right now and go watch that video and then come back. It will provide some really good foundational knowledge about the way an active load circuit works. It's kind of a conceptual leap from combinational logic circuits to sequential logic circuits. And the topic that's often most confusing or hard to grasp for students is the active load. Okay, students, I'm going to assume you watch that video and the concept of an active load is something you A, understand, and we can move forward, or B, you didn't quite understand and you've already contacted me and asked me questions about that. Or C, let's not talk about C. That's a bad option. No, really, I'll gladly jump online in a go-to meeting session with you or a group of you and talk about this. But here's the RS latch. It is the most basic simple storage element. R is used to reset or clear the element on the output. S is used to set the element to a 1. If both R and S are 1, out could be either 0 or 1, which means we have remembered or we have stored, okay? And we're going to talk about the truth table for this in a second, but that was already presented in significant detail in that video that I'm sure you watched, right? I was young once. I know how students behave. Some of you. So here I'm going to walk you through a change in state. We're going to move from one state to the next. We're going to start out with a 1 on the output. So, and you could see that 1 is backfed to A, and we have 1 and 1, and we have the output B backfed to the first NAND gate. So we change R to 0. We want to reset. 0, 0 goes to 1, 1 and 1 are pushed into the NAND gate on S, and A changes to 0. So we've moved from one state to the next. We've reset the latch, the SR latch. Now we're going to start with a 0 on the output. and then we're going to set a 1. So to set a 1, we assert a 0 on the set. That changes the 0 at the outset or the outside of the NAND gate to a 1. The 1 is backfed into A, and R becomes 0. So we've set a 1. To review what was so elegantly covered in the video in the timeline, the RS latch, and this is the real mystical part of this, when R equals S equals 1, we latch, we store the value that was on the output, whether it was a 0 or a 1, to the next state. To set a 1 on the output, S equals 0, R equals 1. To reset the output to 0, R equals 0, S equals 1. The invalid state is R0, S0. Now you're probably thinking, well, how does this thing start up? There is some default startup because it's an active load. And this is why when you turn off the power to a computer, volatile memory loses its contents because it doesn't have an active load, doesn't have current flowing through the circuits. So when you first turn on your computer, there is some default startup mode. And frankly, I don't know what that is. It really doesn't matter. It might be R0, S1, which means there's an active load on this thing. That's most likely what it is, but it's irrelevant to this conversation, and it's not even worth asking. But there is some, when memory is first energized, volatile memory is first energized, there is some current flowing through that, and there is some default startup value. That brings us to the gated delatch. And the gated delatch has some more circuitry to the left of the SR latch that allows us to have two inputs, D and the write enabled signal. WE stands for write enabled. So when write enabled is 1, the latch is set to the value of D. When the write enable is set to 0, the latch holds the previous value, and the value of D is not allowed to pass to the output. You're going to see in adders, multiplexers, various other circuits that the write enable signal is part of the instruction set. And you're going to see very quickly as we get into machine and assembly language, you're going to see certain instructions enable or write enable give us the ability to write a value to a general purpose register. Now I know that's way ahead of where we are now, but I just wanted to say that to get you thinking about this. There are certain instructions that assert a 1 to write enable signal in a gated delatch, which enables us ultimately to write a value to a general purpose register in the processor. Stay tuned. We're going to cover that in extreme detail. But I'm just putting it out there so you're thinking about how this circuitry applies to the programming we're going to learn and do. Learn and do. Okay? Thanks. Sorry. So, as I mentioned previously, those instructions and we've not seen any instructions yet, but those instructions that allow or have the ability to write a value to a register assert a 1 to the right-enabled circuitry. So here's a register. It's a diagram of a 4-bit register. Bit 0, bit 1, bit 2, and 3. That is a collection of D latches, all controlled by a common shared right-enabled signal. When right-enabled is 1, the n bit value, in this case the 4-bit value D, is written, bit 0, bit 1, bit 2, bit 3, is written to the registers bit 0, bit 1, bit 2, bit 3. As we start to talk about multi-bit values, and when we get into the LC3, which is the simulator that allows us to learn x86 assembly and machine language programming, we're going to be talking about bits, 16-bit instructions and 16-bit data, values in data. And there are going to be instances where we want to talk about certain bits in the 16-bit instruction or data. And you'll see the convention A bracket 14:9. That would be the bits 14 to 9 or 9 to 14. This is just a convention, but they do use left to right in the LC3 appendix, which is the manual we're going to be using. So that would designate the bits 14, 13, 12, 11, 10, and 9, which in this instance is going to be 6 bits. We've covered how we store data using bits. And once we have that, we can build a memory. You'll hear me use the term memory map. That was the terminology used when I took assembly language program. I don't know if I ever told you this before, and if I did, just ignore it. But I took an assembly language class, an undergraduate assembly language, machine language assembly language class back in the 1980s. And then when I went to grad school, for some odd reason, that class wouldn't transfer. And I had to take another, years later, I had to take another machine language class that was I think it was a 200 level class. So I've had to take 2 of these classes and then teach it, well, countless times. So anyway, I digress. So now that we can build a memory. The addressability is the number of bits per location. And when you hear about computers that have a 64-bit processor, you hear a 64-bit operating system, that's really an operating system that manages a 64-bit instruction set architecture or a 32-bit instruction set architecture. And things didn't really start happening business-wise, engineering, scientific-wise, for personal computers until we got to the 32-bit version of the x86 instruction set architecture, because then we had 32-bit IEEE 754 floating point decimals. So the addressability is the number of bits per location. The simulator we're going to use simulates the x86 16-bit instruction set architecture, which means every piece of data at any memory location in a register, in the instruction register, in the control unit, being processed by the processor, everything is 16 bits wide. Period. End of conversation. The processor, all the memory, All the registers are all 16-bit wide. It's also called the bus width, those you're into architecture. So that's the addressability, the number of bits per location. And then the number of locations is not usually a power of 2. It's always a power of 2. So we build a logical K times M array of stored bits. And once again, in a 64-bit architecture, the addressability is twice the size of a 32-bit, twice the size of a 16-8. Nobody uses 8. Never really. It really wasn't. That predates me, if you can believe that. And I'm not a young person, young at heart. You can see why, as we start to represent larger structures, we have more abstraction in our diagrams. This is a diagram depicting a 2 squared by 3 memory. 2 squared is 4. So, and you have D0, D1, D2, I'm assuming that is. You've got your right enable word select, your input bits, and your output bits, and then you have your address decoder on the side. And this is how it all comes together. We're getting near the end of the component of this course where we study the concept of architecture, because the course is really it could be named Instruction Set Architectures, ISAs. But we're going to spend, because it's a computer science degree, we're going to spend the majority of our time on the instruction set. But the numbering systems and the conceptual framework regarding basic electronic structures was a much needed review for you as we start to talk about how these things actually go together and how programs write. And I'm really happy with the way the textbook presents this and the sequence of topics that I've taught this course countless times, that we've agreed upon and settled on. The diagram we just reviewed is not the actual implementation, the way memory is implemented. The number of transistors is so much denser than can really be represented in any physical way. But the logical structure is very similar. You got address decoder, word select line, word write enable, and these structures are going to develop more relevance as we bring together the instruction set and the architecture in the remainder of this course. We have 2 basic kinds of volatile random access memory: static, very fast, and DRAM is slower but denser and has to be periodically refreshed. We also have non-volatile memories, ROM, PROM, flash memory. That means memory that doesn't require an active load to hold the contents. Think about it. Your flash drive, you pull it out of the USB port. It has no power source. It has no electrical power source connected to it like the processor does, and it doesn't lose the memory. It's a different animal than volatile memory. It doesn't require an active load. Next important concept is that of a state machine. A machine that moves from one state to the next and can change outputs, can store data, information from one state to the next. So a state machine has a combination. By the way, if we jump to the chase, um, a computer is a state machine, and it has inputs and outputs. It has combinational logic circuits for performing arithmetic logic computations, and it also has storage elements for storing information. Here we have two types of combination locks. One represents a combinational logic or combinational circuit, and the other represents sequential. I've actually owned each one of these locks. I have a lock on my bicycle with a chain, rubberized chain, that is the same as the one on the left. All I need to do, I have a 4-bit or 4-digit combination, and I just simply need to align all the tumblers so that that 4-bit or 4-digit combination is at the top and it opens. And it doesn't matter which way I turn the tumblers, which state they were previously. Now, a sequential combination lock depends on the sequence of values. So let's just say that one has an unlocked combination of 13, 22, 3. Well, it actually has a combination of, let me think about this, 12, then 13. So you have to have 12 and then 13, and then you have to go left, so you have to have 23, then 22, and then 2, and then 3 to unlock it. So it's actually a 6-digit combination. Because if you go left to 13, in other words, 14 and then 13, it's not going to unlock. Even if you then go left to 22 and right to 3, it will not lock. So it's actually based upon the previous state. 13 has to be achieved after a state of 12. And 22 then has to be achieved after a state of 23. And 3 has to be achieved after a state of 2. So the state changes are 12, 13, 23, 22, 2, 3 to unlock that sequential combination lock. I can't stress how important the concept of state is to this class and the remainder of this class. The state of a system is a snapshot of all the relevant elements of the system at the moment the snapshot is taken. So here's a great comparison analogy. The state of a basketball game can be represented by the scoreboard. And there is a clock, just like there is a clock in a computer. The clock in a basketball game is infinitely slower. But the smallest increment of state change for a basketball game is 1 second. And each time that clock ticks down 1 second, the state of the game is different. If no score has been made, it doesn't matter. It could be 38 to 42 with 12 minutes and 10 seconds left in the third quarter, period, whatever. I'm not a baseball fan, different. And it clicks off 1 second and the score is the same, but the state has changed. Okay? The state of a tic-tac-toe game can be represented by the placement of X's and O's on the board. And the smallest increment of state change in a tic-tac-toe game is 1 move. And some people, I guess, do have a timer. I know in chess they have a timer. And you have to move within that I don't know what it is, but I play chess with my daughter-in-law, but we don't use a timer. So walking through the states of the sequential lock. A, the lock is not open and no relevant operations have been performed. B, the lock is not open and the user has completed the R13 operation, meaning clicked on 12 and then 13. C, the lock is not open and the user has completed R13 followed by L22. And then D, I can't remember what the last combination was, but the lock is open. This is a state diagram. It shows all of the possible states of the system being discussed, which is the sequential combinational lock. I'm not going to walk you through all the states. It is fairly straightforward, but just take a look at this and absorb the concept of moving from one state to the other and all of the possible states that could then follow. That brings us to the concept of a finite state machine. Let's cut to the chase. A computer is a finite state machine, albeit many, many, many states, they are finite. So a computer or a finite state machine has a finite number of states, and it moves from one state to the next. A finite number of external inputs, a finite number of external outputs. Explicit specification of all state transitions. How do we move from one state to the next? What causes a state transition? An explicit specification of what determines each external output value. Sometimes, well, you can describe all of this finite state machine sometimes by a state diagram. In essence, we could build a state diagram for a computer, but it would be massive. Inputs typically trigger state transitions, and outputs are associated with each state or with each transition. Next up, the system clock. Frequently, a clock circuit is what triggers a transition from one state to the next. One clock cycle is the smallest increment of state change. Now you'll find as we advance through this course, often the smallest change will involve a single instruction. We will code an instruction for the processor, which is the smallest order we can place at the beginning of the processor. However, you'll find that in most cases, almost all cases, but not all, an instruction takes multiple clock cycles to execute. So, and if you think about a clock on a computer, you typically buy a computer that has, certain parameters. The amount of RAM it has, the computer in front of me has 16 gigabytes of RAM. How much storage it has, 256 gigabytes. And what is the processor speed? And the processor speed is typically represented in megahertz or gigahertz. And those are the number of That's a frequency. Those are the number of clock cycles per second that a computer can change or transition from one state to the next. And if you're talking about gigahertz, you're talking about billions of instructions per second. It is really hard for a human being in a physical world to comprehend the speed at which a computer changes state, the smallest increment, one clock cycle. And things do happen. Actions are performed in a single clock cycle. Now we have more components necessary for the implementation of a finite state machine. We have inputs, we have our outputs, we have our combinational logic circuits which perform work, arithmetic logic computations. We have our storage elements, and we have our composer, which is the clock. The combinational logic circuits are used in determining outputs in the next state. The storage elements maintain state representation, and the clock, of course, is the composer. It manages the increment of time necessary for one state or changes from one state to the next. Let's take a look at a master-slave flip-flop, which is a pair of gated D-latches that isolate the next state from the current state. Now notice there's a lot going on in this slide, so stay with me. So we have input coming from a combinational logic circuit. And this is just for one bit from the combinational logic circuit on the right. And so we have the clock double fed, cross fed into latch B directly, and notice it gets inverted. The signal for the clock gets inverted before it's sent to latch A. This is the right enabled signal. So you need a 1 on that right enabled signal in order for it to pass the input to the output of the gated D latch. So during the first phase, when the clock is 1, okay, we have the previously computed state, which was sent from the combinational logic circuit on the right into latch A, sitting there. It will be written into or written through latch B, and it becomes the current state sent to the logic circuit on the left. Because that 1 enables latch B to pass it through. At the same time, the 1 becomes a 0 and nothing happens in latch A. Now during the second phase, right, when the clock goes to 0, it's a series of 1 0 1 0 1 0. That's the pulses, if you will. Latch B is isolated because the right enabled is asserted as 0. A 0 is asserted on the right enabled signal for latch B, and a 1 is asserted on latch A, because remember, 0 becomes 1, 1 becomes 0. So then the next state computed by the logic circuit is stored in latch A, ready to become the current state when the clock cycles. As I mentioned in the previous slide, each of the master-slave flip-flop circuits stores just one bit. So for the instruction set architecture in the computer in front of me, we would have 64 of those to be able to match the 64-bit architecture, bus size, if you will. The number of storage elements flip-flops needed is determined by the number of states and the representation of each state. Some examples, a sequential lock had 4 states, so we'd need 2 bits. Basketball scoreboard, we need 7 bits for each score, 5 bits for minutes, 6 bits for seconds, 1 bit for possession arrow, 1 bit for half, etc., etc., etc. Here we see an example of a blinking traffic sign. When it blinks a pattern from left to right, first state is lights 1 and 2 are on, second state 1, 2, 3, and 4 are on, third state 1, 2, 3, 4, 5, and on. This will repeat as long as the switch is turned on. Before I speak to this diagram, which is the state diagram for the traffic sign we just looked at, I want to make sure you understand why we're spending this much time on state. When we get to the programming component of this class and we start programming in machine language, one of the things we're going to be able to do because of this wonderful simulator we have, the LC3, is we're going to be able to take state snapshots. We're going to be able to step through a machine language instruction and pause the processor. That is almost impossible to do without some sort of simulation tool like we have. Things happen really quick, and there's a significant amount of information that you'll miss without being able to stop the machine and take a state snapshot. And in some cases, I'm going to show you how we can actually dump main memory into a text file, and we could look at the contents of all the registers, the program counter, the instruction register, all of that. So the concept of state and moving from one state to the next is a critical component for understanding the information processing cycle. So here we have the state diagram for the traffic sign we just saw, and all of the possible states and the transitions between the states. You can see all off, the switch is on, we go to state number 1, 1 and 2 on. If we turn the switch off, we go back to 0, 0. If the switch is still on, we transition from 1, 0, 1 to 1, 0. If the switch is still on, we go to 1, 1. If the switch is turned off, we go back to 0, 0, etc., etc., etc. It is important that you understand that all of these are valid states, and the paths between those states are valid state transitions. And here we see the accompanying truth table for the 2 bits S1 and S0 and all of the possible states that can be achieved with 2 bits. Getting close to the end, my friends. I know the topics covered in this lecture and in the numbering systems lecture seem tedious, cryptic, and yes, they are, but they are necessary to build the conceptual framework needed for us to move forward into the programming piece. So here we have implementation of the traffic sign logic. You see the input, C, ZY, and X, and S0 and S1 fed back into the storage element to isolate the next state from the current state. Take a minute, pause this, take a minute, and review this and walk yourself through. If you want the truth table, print the truth table on the previous slide and just walk through so you can see how this works. Moving on from logic to data path. The data path of a computer is all of the logic used to process information. We're going to see a data path, albeit with a lot of abstraction, data path for the LC3 on the next slide, which is the simulator, the x86 simulator that we're going to be using in this class. So we have the combinational logic circuits, the decoder convert instructions into control signals, multiplexers select specific inputs and outputs, the arithmetic logic unit, which really is the part of the processor that performs work, if you will. It actually performs computation. And then we have our sequential logic. We've got a state machine that coordinates control signals and the data movement, and we have registers and latches as storage elements. Although this diagram looks very complex, there's actually a very significant level of abstraction in this. We're not representing any components. A lot of these boxes that you see in the diagram are extremely complex devices. The arithmetic logic unit, for example. So just in closing, and this is the last slide of this lecture, we have a state machine, we have storage units, and we have combinational logic circuits that all work together to create or to implement a finite state machine. And although finite sounds easily quantifiable, it's a pretty significant number of states that a computer can assume, be in, etc. It's not something that we could really represent completely, easily in a state diagram. Thanks for watching. Of course, if you have any questions, ping me any of the multiple ways, and I'll work through any questions you have on any of this material. Thanks for watching, and have a great day.